Right now, as you read this, you're hurtling through space at 67,000 miles per hour on a rock orbiting an unremarkable star in an ordinary galaxy among 2 trillion others. In this vast cosmic arena containing more stars than grains of sand on all Earth's beaches, you are completely, utterly alone. Or are you? Picture this. It's 3 a.m., and you're lying in bed staring at the ceiling, wrestling with insomnia and existential dread. Your mind wanders to that age-old question that has haunted humanity since we first looked up at the stars and wondered if anyone was looking back. But here's the thing. This isn't just some abstract philosophical puzzle you ponder during sleepless nights. This is potentially the most important question our species has ever asked, and the answer could determine whether we have a future at all. Welcome to the Fermi Paradox, named after the brilliant physicist who casually asked a question that would torment scientists for decades. Where is everybody? It's a deceptively simple question that opens up a cosmic can of worms so disturbing, so mind-bending, that it makes your 3 a.m. anxiety look like a warm hug from your grandmother. Let's start with some numbers that should make your brain hurt. The observable universe, that's just the part we can actually see, stretches 93 billion light-years across and contains an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Our own Milky Way has somewhere between 100 to 400 billion stars, and virtually every single one of them has planets. That's not speculation anymore. That's confirmed fact thanks to the Kepler Space Telescope and other planet-hunting missions. But wait, it gets worse. Recent calculations suggest there are roughly 40 billion Earth-sized planets in the habitable zones of sun-like stars in our galaxy alone. That's 40 billion worlds where liquid water could exist, where life as we know it could potentially flourish. And that's just in our neighborhood. Multiply that by 2 trillion galaxies, and you're dealing with numbers so large they become meaningless to the human brain. Here's where it gets really unsettling. If even a tiny fraction of those planets developed life, and if even a minuscule percentage of those developed intelligence, and if just a handful of those became spacefaring civilizations, the universe should be absolutely teeming with aliens. We should be getting alien spam calls. The night sky should be lit up like a cosmic Las Vegas with the signatures of advanced civilizations. We should be tripping over alien artifacts every time we step outside. But we're not. The universe is silent. Eerily, terrifyingly silent. This silence isn't just puzzling, it's mathematically impossible. Frank Drake worked out the equation in 1961, and even with conservative estimates, there should be millions of detectable civilizations in our galaxy alone. Carl Sagan, that eternal optimist, believed the galaxy was practically crawling with intelligent life. Yet after more than 60 years of searching with increasingly sophisticated technology, we found nothing. Not a single confirmed signal. Not one artificial structure. Not even a piece of space junk that screams, made by aliens. The silence is so complete, so absolute, that it's become a scientific crisis. We call it the Fermi Paradox, but it's really more like the Fermi Nightmare. Because if the universe should be full of life but appears empty, something is very, very wrong with our assumptions. And that something might involve humanity's future in ways that will keep you awake at night. Consider the possibilities, each more chilling than the last. Maybe life is incredibly rare, and we're one of the few planets where it managed to emerge. Maybe intelligence is even rarer, and we're freakishly unique in our ability to contemplate the cosmos. Maybe technological civilizations destroy themselves so quickly that they never get the chance to spread across the galaxy. Maybe something out there is hunting them down, silencing them one by one. Or maybe, and this is perhaps the most disturbing possibility, maybe they're all around us, watching us like we're animals in a zoo, waiting for us to reach some cosmic milestone before making contact. Maybe we're not advanced enough, not civilized enough, not worthy enough to join the galactic community. The recent explosion in UFO reports and government disclosures has only made this more unsettling. For decades, anyone who claimed to see a UFO was dismissed as a crackpot. Now, the Pentagon is releasing videos of objects that appear to defy the laws of physics, and former military officials are testifying before Congress about encounters with craft that exhibit impossible flight characteristics. Are we finally getting glimpses of the intelligence that has been hiding in plain sight? But here's what really should make your skin crawl. we might be living through the most dangerous period in human history. Many scientists believe we're approaching what they call the Great Filter, a point in the evolution of intelligent life where most species either transcend to become something unimaginably advanced or destroy themselves completely. And we might be about to find out which side of that cosmic coin flip we're on. The development of artificial intelligence, something that could happen within the next few decades, might be the ultimate test. If most alien civilizations create AI before learning to control it, that could explain the silence. They might all be extinct victims of their own technological success. Or they might have transcended biology entirely, becoming something so advanced that they're invisible to us, like gods contemplating ants. This isn't just about aliens anymore. It's about us. It's about whether humanity will survive the next century, whether we'll become one of the rare species that makes it past the Great Filter, or whether we'll become just another brief silence in the cosmic void. The universe is vast, ancient, and filled with possibilities we can barely imagine. But it's also filled with dangers we're only beginning to understand. The search for extraterrestrial intelligence isn't just a scientific endeavor. It's a search for our own future, a glimpse into the cosmic mirror that will show us what we might become or what we might never be. So as you lie in bed tonight, staring at the ceiling and wondering about your place in the universe, remember this. The silence isn't just puzzling. It's a warning, and we're running out of time to figure out what it means. But before we dive deeper into this cosmic nightmare, let's go back to where it all started. Because like most world-changing ideas, this one began not in a laboratory or observatory, but over lunch. And the man who asked the question that would haunt humanity for decades wasn't even thinking about aliens when he said it. Picture this. It's the summer of 1950, and the world is still reeling from the atomic age that was unleashed just 5 years earlier. At Los Alamos National Laboratory in New Mexico, the same place where humanity first split the atom and changed the course of history, a group of brilliant physicists are walking to lunch like they do every day. But this isn't just any group of scientists. These are the minds that literally reshaped reality, the men who figured out how to harness the power of the sun and put it into a bomb. Leading the pack is Enrico Fermi, a man so brilliant that his colleagues called him the Pope of Physics. This is the guy who built the first nuclear reactor in a squash court under the University of Chicago, who could solve complex mathematical problems in his head while others struggled with calculators. Fermi had a habit of asking seemingly simple questions that would unravel into profound mysteries. Questions like, how many piano tuners are there in Chicago? Or, how much energy would it take to lift a human being into orbit? These weren't just idle curiosities. They were mental exercises that revealed deep truths about the world. Walking with Fermi that day were Edward Teller, who would later become known as the father of the hydrogen bomb, Emil Konopinski, and Herbert York. They're strolling through the high desert landscape of New Mexico, probably discussing the latest developments in nuclear physics, when the conversation takes an unexpected turn. They'd been talking about UFOs. Yes, you heard that right. Even the world's most brilliant physicists were gossiping about flying saucers. The year 1950 was right in the middle of the first great UFO wave that swept America. Reports of strange objects in the sky were making headlines, and everyone had an opinion about what they might be. The scientists had also seen a humorous cartoon in The New Yorker showing aliens stealing trash cans from New York City streets, which had given them a good laugh. But here's where the story gets interesting, because what happened next has been twisted and mythologized beyond recognition. They settled down for lunch at the Fuller Lodge, probably complaining about the food like anyone else would. The conversation drifts from UFOs to the broader question of life in the universe. And that's when Fermi, almost as an afterthought, asks the question that would define the rest of his career and launch 1,000 scientific papers. Where is everybody? For simple words. But those 4 words contained within them the seeds of one of the most profound scientific mysteries of our time. Fermi wasn't making a grand proclamation about the absence of alien life. He wasn't laying out a formal argument about why the universe should be teeming with civilizations. He was just wondering, the way you might wonder why your favorite restaurant is empty on a Friday night, or why your phone hasn't rung all day. But here's the thing that most people don't know about this famous moment. Fermi probably wasn't even thinking about what we now call the Fermi paradox. According to the 3 surviving witnesses who were interviewed decades later, Fermi was actually questioning whether interstellar travel was even possible. He was doing what he did best, taking a complex problem and reducing it to its essential elements. Edward Teller, who was there that day, later recalled, "I do not believe much came from this conversation, except perhaps a statement that the distances to the next location of living beings may be very great and that, indeed, as far as our galaxy is concerned, we are living somewhere in the sticks, far removed from the metropolitan area of the galactic center." Think about that for a moment. Fermi wasn't declaring that aliens don't exist. He was suggesting that we might be living in the cosmic equivalent of a small town in Montana, too far from the action to notice what's happening in the big city. It's a remarkably humble and prescient observation from a man who had just helped humanity enter the atomic age. But like all great ideas, this one took on a life of its own. The question that Fermi asked wasn't formally turned into what we now call the Fermi paradox until 1975, when astronomer Michael Hart wrote a paper titled An Explanation for the Absence of Extraterrestrials on Earth. Hart argued that any technological civilization would inevitably colonize the entire galaxy within about 10 million years, even traveling at just 1% the speed of light. Hart's logic was brutally simple. If aliens existed anywhere in the galaxy, they would have had plenty of time to reach Earth. Since they're not here, they must not exist. It was a conclusion that would have probably surprised Fermi, who was known for his optimism about the possibilities of science and discovery. The argument was refined in 1980 by physicist Frank Tipler, who calculated that self-replicating robotic probes could explore the entire galaxy in less than 300 million years. Tipler's conclusion was even more stark. The absence of such probes proved that we are alone in the universe. This became known as the Hart-Tipler argument, though most people called it the Fermi paradox. But here's the irony that would probably amuse Fermi. The Fermi paradox isn't really Fermi's, and it's not really a paradox. It's more like the Hart-Tipler assumption, based on a Fermi question. The man who asked, "Where is everybody?" was approaching the problem like the brilliant physicist he was, by questioning our assumptions and looking for the variables we might be missing. Fermi died in 1954, just 4 years after that famous lunch, so we'll never know what he would have thought about the elaborate theories that grew from his simple question. But knowing Fermi's personality and his approach to problems, he probably would have been fascinated by the possibilities rather than depressed by the silence. Because that's what made Fermi special. He didn't just accept the obvious answers. He kept digging, kept questioning, kept wondering. And in doing so, he gave us a question that continues to challenge everything we think we know about life, intelligence, and our place in the cosmos. That casual lunch conversation in 1950 set in motion a chain of thinking that would revolutionize how we approach the search for extraterrestrial intelligence. It spawned new fields of study, launched countless research projects, and continues to drive some of the most ambitious scientific endeavors in human history. But most importantly, it reminded us that the biggest discoveries often come from the simplest questions. Sometimes all it takes is someone brave enough to ask, "Where is everybody?" 11 years after Fermi's casual question echoed through that Los Alamos dining hall, a young astronomer named Frank Drake decided to do something that would either be remembered as brilliantly ambitious or spectacularly naive. He was going to try to answer Fermi's question with mathematics. And in doing so, he would create what might be the most famous equation in science that produces absolutely useless results. Picture this. It's November 1961, and you're driving through the mountains of West Virginia toward the Green Bank Observatory. The roads are winding, the autumn leaves are spectacular, and you're about to attend what might be the most important scientific meeting that nobody has ever heard of. The official title is dry and academic, Conference on Extraterrestrial Intelligent Life. But the 10 scientists gathering for this historic meeting have given themselves a much more colorful name, the Order of the Dolphin. Why dolphins? Because one of the attendees, neurologist John Lilly, had recently made headlines with his research on dolphin communication. If we could figure out how to talk to dolphins, the thinking went, maybe we could figure out how to talk to aliens. It was the kind of optimistic, boundary-pushing thinking that defined the early 1960s. A time when it seemed like science could solve any problem, answer any question, unlock any mystery. The man who organized this gathering was Frank Drake, and he had a problem. Not a mathematical problem, mind you, Drake was brilliant with numbers. His problem was much more basic. How do you structure a scientific discussion about something that might not exist? How do you have a meaningful conversation about extraterrestrial intelligence when you have zero confirmed examples to work with? Drake's solution was elegantly simple and would make him famous. The night before the meeting, he sat down with a piece of paper and sketched out an equation that would break down the problem into manageable chunks. He later said he spent all of 10 minutes on it, scribbling variables that seemed relevant to the question of how many communicating civilizations might exist in our galaxy. The next morning, Drake walked into the meeting room and wrote his equation on the blackboard. It was beautiful in its simplicity. Each variable represented a step in the chain from stellar formation to galactic conversation. R was the rate of star formation in our galaxy. Fp was the fraction of those stars that have planets. Ne was the number of planets per star system that could potentially support life. Fl was the fraction of those planets where life actually appears. Phi was the fraction of life-bearing planets where intelligent life emerges. Fc was the fraction of civilizations that develop technology capable of releasing detectable signs into space. And L was the length of time such civilizations release detectable signals. The equation was essentially asking, how many ways can the universe make beings like us? The scientists gathered around that blackboard, including a young Carl Sagan, who would later become the public face of the search for extraterrestrial intelligence, began plugging in numbers. And what they found was simultaneously thrilling and terrifying. Let's walk through their thinking, because it reveals just how reasonable it seemed to expect a galaxy teeming with intelligence. They estimated that about 10 new stars formed in our galaxy each year. Maybe half of those had planets, a conservative guess in 1961, before we knew that planets were actually everywhere. Of those planetary systems, maybe 2 planets per system were in the habitable zone where liquid water could exist. Here's where it gets interesting. The early estimates for the fraction of suitable planets that actually develop life were surprisingly optimistic. Remember, this was 1961, and scientists were still riding high on the discovery of DNA and the growing understanding of how life works at the molecular level. Life seemed like a natural consequence of the right chemical conditions, not some miraculous accident. The fraction of life-bearing planets that develop intelligence? The scientists figured that evolution naturally tends toward greater complexity and intelligence. Look at Earth. In just a few billion years, we'd gone from single-celled organisms to beings capable of contemplating the universe. Surely that was a common trajectory. The fraction of intelligent species that develop detectable technology? Well, here they were, a species that had developed radio telescopes within decades of discovering electricity. It seemed like a natural progression. When they plugged in their numbers, estimates that seemed reasonable at the time, they got a stunning result. The Drake equation suggested there should be somewhere between 20 and 50 million communicating civilizations in our galaxy. Million. Not dozen, not hundred, not thousand. Million. Carl Sagan, ever the optimist, thought the numbers might be even higher. He estimated that there could be up to 1 million civilizations in our galaxy advanced enough to engage in interstellar communication. The galaxy, according to their calculations, should be absolutely buzzing with alien chatter. But here's where the story takes a darker turn. Armed with these optimistic predictions, scientists began listening, and listening, and listening some more. They built bigger telescopes, developed more sensitive receivers, expanded their search to cover more frequencies and more star systems. They listened for decades, scanning millions of star systems, processing vast amounts of data, hoping to catch even the faintest whisper of an alien signal. And they heard nothing. Absolutely nothing. The silence was deafening. It was as if the universe was playing a cosmic joke on them. The math said there should be millions of civilizations out there, but the sky remained stubbornly, mysteriously quiet. Every year that passed without a detection made the mystery deeper and more troubling. The problem, as Drake later realized, was that most of the variables in his equation were essentially unknown. We could measure the rate of star formation and estimate how many stars have planets, but everything else was pure speculation. The fraction of planets where life appears. We had exactly one example to work with, the fraction where intelligence emerges. Again, one example, the average lifetime of a communicating civilization? We've been broadcasting for less than a century. We had no idea how long civilizations typically last. The Drake equation, it turned out, was less a tool for calculating the number of alien civilizations and more a way of organizing our ignorance. Each variable represented a profound gap in our understanding of life, intelligence, and the cosmos itself. But perhaps that was the point. The equation didn't give us answers, it gave us the right questions to ask. It laid out a research program that would drive the search for extraterrestrial intelligence for decades to come. Every variable in the equation represented a field of study, a line of inquiry, a piece of the puzzle that might eventually reveal why the universe seems so empty. The silence wasn't just puzzling anymore. It was becoming a crisis, and scientists began to realize that the answer to Fermi's question might be far more disturbing than anyone had imagined. Those scary theories didn't take long to materialize, and when they did, they made the cosmic silence feel less like a mystery and more like a warning from the universe itself. The most terrifying of these theories came from an unlikely source, an economist named Robin Hanson who looked at the Drake equation's disappointing results and asked a question that would make your blood run cold. What if there's something out there killing civilizations before they can spread across the galaxy? It was 1996, and Hansen was working at the Future of Humanity Institute when he published a paper with the innocuous title, The Great Filter, Are We Almost Past It? But don't let the academic language fool you. This paper contained one of the most chilling ideas in the history of science. The possibility that somewhere in the long chain from lifeless matter to galaxy-spanning civilizations, there exists an evolutionary bottleneck so narrow, so deadly, that it acts like a cosmic exterminator. Hansen called this bottleneck the Great Filter, and his logic was brutally simple. If life is common in the universe, and if intelligence naturally evolves from life, and if intelligent civilizations naturally expand across the galaxy, then the galaxy should be teeming with aliens. Since it's not, something must be preventing most life from making it to the galactic expansion stage. Something is filtering out civilizations before they can spread. But here's where it gets truly terrifying. We don't know where this filter is located in the evolutionary chain. And depending on where it sits, humanity might be either incredibly lucky or absolutely doomed. Picture evolution as a ladder with 9 critical rungs, each one representing a step so improbable that most attempts fail. Hansen mapped out these steps with the cold precision of someone calculating the odds of survival in a cosmic lottery. Step 1. The right star system. You need a star that's stable, long-lived, and has planets in the habitable zone. Sounds easy, right? But most stars are either too hot, too cold, too variable, or too short-lived. Many are in binary systems where planets can't maintain stable orbits. Others are in regions of the galaxy where radiation levels would sterilize any life that tried to emerge. Step 2. Reproductive molecules. This is where chemistry becomes biology. You need self-replicating molecules like RNA or DNA to emerge from the primordial soup. It sounds inevitable, but think about it. You're asking random chemical reactions to spontaneously create information storage and transmission systems. It's like expecting a tornado in a junkyard to assemble a working computer. Step 3. Simple single-celled life. Even with self-replicating molecules, you need to build the first actual living cells. This requires developing cell membranes, metabolism, and all the basic machinery of life. On Earth, this step happened relatively quickly after the planet cooled down, which might mean it's either easy or we got incredibly lucky. Step 4. Complex single-celled life. This is where things get really interesting. For almost 2 billion years, Earth was populated only by simple bacteria and archaea. Then, in what biologists call the Great Oxidation Event, some cells learned to use oxygen and developed complex internal structures. This transition to eukaryotic cells was so dramatic that it fundamentally changed the planet's atmosphere and paved the way for everything that followed. Step 5. Sexual reproduction. Life needed to figure out how to mix genetic material from different organisms. This seems obvious to us, but for billions of years, life reproduced only through simple cell division. Sexual reproduction dramatically accelerated evolution by allowing beneficial mutations to spread and harmful ones to be filtered out. Step 6. Multicellular life. Individual cells had to learn to cooperate and specialize. This transition happened multiple times on Earth, But it took billions of years and required solving complex problems of cellular communication and coordination. Most attempts at multicellularity failed, leaving only a few successful lineages. Step 7. Tool using animals with large brains. Intelligence isn't just about having a big brain. You need the right kind of intelligence in the right kind of body with the right kind of social structure. Dolphins are intelligent but lack manipulative appendages. Octopi are incredibly smart but are solitary and short-lived. It took a very specific combination of factors to produce a species that could develop technology. Step 8. Where we are now, we've developed technology, but we haven't yet spread beyond our home planet in any meaningful way. We're still a single point of failure, vulnerable to asteroids, supervolcanic eruptions, nuclear war, climate change, or any number of existential threats. Step 9. Explosive, lasting expansion. This is the step that would make us detectable to other civilizations. We need to spread across the galaxy, building structures and sending signals that would be obvious to any other technological species. This is what the Drake equation was trying to calculate, and it's what we haven't seen any evidence of. Now here's the truly terrifying part. We don't know which of these steps represents the Great Filter, and that uncertainty could determine whether humanity has a future or is about to hit a cosmic wall. If the Great Filter is behind us, say, in the transition from simple to complex cells, then we're extraordinarily lucky to exist, but we might be alone in the galaxy. Earth could be one of the few planets where life managed to navigate the early evolutionary challenges. In this scenario, the universe might be full of planets with simple life but almost no complex organisms, let alone intelligence. But if the Great Filter is ahead of us, then we're in serious trouble. Maybe most civilizations develop nuclear weapons before they develop the wisdom to avoid using them. Maybe they trigger unstoppable climate change. Maybe they create artificial intelligence that decides biological life is obsolete. Maybe they fall victim to some other technological trap that we haven't even thought of yet. The most unsettling possibility is that the Great Filter is right in front of us, and we're about to discover what it is. Some scientists think the development of artificial intelligence might be the ultimate filter. If most civilizations create AI before learning to control it, they might face extinction or transformation into something unrecognizable. The window between developing AI and either mastering it or being mastered by it might be measured in decades, not centuries. This creates a paradox that keeps researchers awake at night. Every piece of evidence that life is common in the universe makes our own future look more precarious. Every discovery of potentially habitable planets, every detection of organic molecules in space, every sign that the early steps of evolution might be easy increases the probability that the Great Filter lies ahead of us. We've been assuming that intelligence is evolution's great achievement, but what if it's evolution's great mistake? What if the very traits that make us human, our curiosity, our tool-making abilities, our drive to understand and control our environment, are the same traits that doom most civilizations? The silence from the stars might not be a mystery waiting to be solved. It might be a warning about what's coming for us. But what if we've been thinking about this all wrong? What if the reason we haven't heard from alien civilizations isn't because they're extinct, but because they're deliberately avoiding us? What if right now, as you're reading this, there are beings watching our planet the same way we watch animals in a nature preserve, with interest, perhaps even affection, but with a strict policy of non-interference? Welcome to one of the most unsettling solutions to the Fermi paradox, the zoo hypothesis. And before you dismiss it as science fiction nonsense, consider this. It's one of the few theories that actually explains both the mathematical prediction of abundant alien life and the observed silence of the cosmos. It suggests that the universe might be teeming with intelligence, but that intelligence has collectively decided that humanity isn't ready for contact. The idea was first proposed in 1973 by MIT astrophysicist John Ball, who was grappling with the same contradiction that had puzzled scientists since Drake's equation. If aliens should exist, why haven't we found them? Ball's answer was elegantly simple and deeply disturbing. They're here, but they're hiding. Picture this scenario. You're walking through Yellowstone National Park, and you come across a pack of wolves. Do you walk up to them and try to start a conversation? Do you show them your smartphone and try to explain quantum mechanics? Of course not. You observe them from a distance, maybe take some photos, and try not to disturb their natural behavior. Now imagine that you're the wolf, and somewhere in the trees, something infinitely more intelligent than you is watching, studying, and carefully avoiding contact. Ball proposed that Earth might be part of a galactic wilderness area, or zoo, where intelligent life is allowed to develop naturally without outside interference. Advanced civilizations might have policies similar to Star Trek's Prime Directive: no contact with primitive species until they reach certain technological, ethical, or social milestones. But here's where it gets really interesting. The zoo hypothesis has spawned several variations, each more thought-provoking than the last. There's the laboratory hypothesis, which suggests we're not just being observed but actively studied, like bacteria in a petri dish. Maybe our entire history, our wars, our scientific discoveries, our cultural evolution, is all part of some vast experiment designed to understand how intelligence develops. Then there's the planetarium hypothesis, which proposes something even more unsettling: that our entire perceived universe might be artificially created to hide the truth from us. We think we're looking at a vast, empty cosmos, but we might actually be surrounded by a bustling galactic civilization that's been carefully concealed from our view. Every time we point our telescopes at the sky, we might be seeing a carefully crafted illusion designed to make us think we're alone. The most disturbing variation might be the temporal zoo hypothesis, which suggests that the non-interference policy is temporary. Maybe contact will happen when we reach certain developmental markers, when we stop fighting wars, when we solve climate change, when we develop interstellar travel, or when we create artificial intelligence that doesn't destroy us. We might be in a cosmic waiting room, and we don't even know what test we're supposed to pass. Now, you might be thinking this all sounds like paranoid conspiracy theory material, and you'd be right to be skeptical. The zoo hypothesis faces some serious scientific challenges. Dr. Duncan Forgan at the University of St. Andrews has shown that maintaining galactic-scale secrecy would be nearly impossible. Any civilization advanced enough to monitor thousands of developing species would need to coordinate policies across millions of member worlds. Messages would take tens of thousands of years to cross the galaxy, making real-time coordination impossible. But here's what makes the zoo hypothesis particularly compelling right now: the recent explosion in UFO sightings and government disclosures. For decades, anyone who claimed to see a UFO was dismissed as a crackpot or attention seeker. But something has changed. The Pentagon has released videos of objects that seem to defy the laws of physics. Former military officials are testifying before Congress about encounters with craft that exhibit impossible flight characteristics: instantaneous acceleration, hypersonic speeds without sonic booms, and maneuvers that should destroy any known aircraft. The Pentagon's 2024 UAP report documented 757 new sightings, with 21 classified as true anomalies that resist conventional explanation. These aren't grainy photos taken by drunk farmers anymore. These are high-definition videos captured by military sensors, witnessed by trained pilots, and documented by multiple independent systems. Could this be evidence of the zoo hypothesis in action? Maybe the zookeepers are getting sloppy, or maybe they're gradually preparing us for contact. Maybe those UAP sightings are like glimpses of zoo staff moving between exhibits, usually hidden but occasionally visible to the more observant animals. But before you start scanning the skies for alien spacecraft, remember that extraordinary claims require extraordinary evidence. The vast majority of UFO sightings have conventional explanations, whether balloons, aircraft, satellites, or natural phenomena. Even the most puzzling cases could be advanced human technology, measurement errors, or atmospheric effects we don't fully understand. The zoo hypothesis also raises profound questions about human nature and our place in the cosmic order. If we're being watched, what do our observers think of us? Are we the cute, harmless species that they enjoy watching? Or are we the dangerous, unpredictable animals that need to be contained? Are we passing their tests? Or are we failing spectacularly? Consider what an alien civilization might see when they observe humanity. They'd see a species that discovered atomic energy and immediately used it to build weapons. They'd see us depleting our planet's resources, driving other species to extinction, and struggling to cooperate even in the face of global threats like climate change. They'd see us developing artificial intelligence without adequate safeguards, creating technologies that could enhance or destroy our civilization. Maybe the zookeepers are waiting for us to prove we're responsible enough for contact. Maybe they're waiting for us to stop being a threat to ourselves and other potential civilizations. Maybe they're waiting for us to develop the wisdom to handle the knowledge that we're not alone. Or maybe, and this is perhaps the most humbling possibility, maybe they're waiting for us to become interesting enough to bother with. Maybe humanity is still in its intellectual infancy, and our current level of technology and understanding is about as impressive to them as a child's finger painting is to us. The zoo hypothesis forces us to confront an uncomfortable truth. We might not be the crown of creation we think we are. We might be cosmic toddlers, stumbling around in a universe full of grown-ups who are politely waiting for us to mature before they introduce themselves. But there's another possibility that's even more chilling than being ignored by benevolent zookeepers. What if the universe isn't a zoo at all, but something far more terrifying? What if it's a dark forest where every intelligent species is a hunter, moving silently through the trees, knowing that the first to make a sound will be the first to die? This isn't the paranoid fantasy of a science fiction writer, though it was popularized by one. It's a cold, logical theory that might explain why the cosmos is so eerily quiet, and why humanity's attempts to broadcast our existence might be the most dangerous thing our species has ever done. The dark forest theory emerged from the brilliant mind of Chinese author Liu Cixin, but it's built on a foundation of game theory and evolutionary psychology that makes it disturbingly plausible. Liu didn't just create a scary story. He identified what might be the most fundamental law of cosmic sociology, a principle so basic and so brutal that it could govern the behavior of every intelligent species in the universe. The theory starts with three simple axioms that seem almost self-evident, but when combined, they create a logical chain that leads to a horrifying conclusion. Axiom 1. Survival is the primary need of all civilizations. This seems obvious, right? Any species that doesn't prioritize survival won't last long enough to develop technology, let alone spread across the galaxy. Evolution has hardwired this imperative into every living thing on Earth, from bacteria to blue whales. Why would intelligent aliens be any different? Axiom 2. Civilizations continuously expand, but universe resources remain constant. Again, this feels like common sense. Growing populations need more resources, more space, more energy. Even if a civilization develops incredible efficiency, there are still fundamental limits imposed by physics. Eventually, expanding civilizations will come into competition for the same resources. Axiom 3. Civilizations cannot determine others' intentions with certainty. This is the killer. Even if you encounter another civilization that seems peaceful, how can you be sure they'll stay that way? How can you know they won't develop weapons that could destroy you? How can you predict what they'll do when their own survival is threatened? From these three axioms, Liu derived a conclusion that should make your blood run cold. The universe is like a dark forest where every civilization is an armed hunter, stalking silently through the undergrowth. The hunter knows that other hunters are out there, but he doesn't know where they are or what their intentions might be. The only thing he knows for certain is that if he reveals his position, he might be destroyed by someone who sees him as a threat. In this cosmic game of survival, the optimal strategy is terrifyingly simple. Stay hidden, and if you do discover another civilization, destroy it immediately before it can destroy you. Not because you're evil, not because you're aggressive, but because you can't take the risk of being wrong about their intentions. The logic is grimly compelling. Imagine you're the leader of a civilization that has just detected radio signals from another world. What do? You can't communicate with them. By the time your message reaches them and they respond, centuries might have passed. You can't assess their true intentions. They might be peaceful now, but what about in 1,000 years? You can't predict their technological development. They might develop weapons that could wipe out your entire species. But you do know one thing. They've revealed their location. And in a universe where resources are finite and intentions are unknowable, that makes them a potential threat to your survival. The safest course of action, the one that maximizes your chances of long-term survival, is to destroy them before they can develop the capacity to destroy you. This creates what game theorists call a chain of suspicion. You don't know if they're hostile, but you can't be sure they're not. They don't know if you're hostile, but they can't be sure you're not. Each side has to assume the other might be a threat, And in a universe where the stakes are extinction, it's better to be safe than sorry. The dark forest theory explains the cosmic silence perfectly. Any civilization that broadcasts its location is essentially painting a target on itself. The smart civilizations, the ones that survive, are the ones that keep quiet. They develop their technology in secret, explore the galaxy with stealth, and eliminate any potential threats before those threats can eliminate them. It's a paranoid's vision of the universe, but it's also logically consistent. If every civilization follows this logic, then the galaxy could be full of advanced intelligences that are all hiding from each other. The absence of detectable signals doesn't mean the absence of intelligence. It means the presence of intelligent species that are smart enough to keep their mouths shut. But here's where it gets truly terrifying for humanity. We've been broadcasting our existence for over a century. Every television show, every radio program, every radar pulse has been leaking into space, announcing to anyone who's listening that there's an intelligent species on Earth. If the dark forest theory is correct, we've been painting targets on ourselves for decades. Our first television broadcasts are now about 100 light-years away from Earth, meaning that any civilization within that sphere might already know we exist. Our most powerful radio telescopes could detect signals from civilizations thousands of light-years away, so it's reasonable to assume that advanced civilizations could detect our signals from similar distances. According to dark forest logic, any civilization that detected our signals would have to make a choice. Ignore us and hope we never become a threat, or eliminate us before we develop the capacity to threaten them. The theory suggests that the second option is the rational choice. Now, critics of the dark forest theory point out several problems with this logic. If everyone is hiding, who's doing the destroying? The theory assumes that detection automatically leads to destruction, but that might not be true for truly advanced civilizations. And it relies heavily on assumptions about resource scarcity that might not apply to civilizations capable of stellar engineering or matter conversion. But the theory has gained serious consideration from scientists and philosophers because it addresses a fundamental problem in thinking about alien contact. How do you establish trust with a civilization that you can't communicate with in real time, whose intentions you can't verify, and whose technological capabilities you can't predict? The dark forest theory also raises uncomfortable questions about humanity's own SETI efforts. By actively searching for alien signals and broadcasting our own, are we making ourselves safer or more vulnerable? Are we trying to join a galactic community? Or are we stumbling blindly into a cosmic war zone? Maybe the silence from the stars isn't a mystery to be solved. Maybe it's a survival strategy that we should be copying instead of breaking. Maybe the universe is full of civilizations that have learned to be very, very quiet. But what if we've been thinking about this entirely wrong? What if the reason we don't see alien civilizations isn't because they're hiding or extinct, but because they've transcended physical reality entirely? What if we're looking for biological beings in a universe that has moved beyond biology, searching for radio signals from civilizations that communicate in ways we can't even imagine? This possibility is more than just science fiction speculation. It's becoming the mainstream view among many SETI researchers. And it suggests that we might be living through the most important transition in the history of life itself. The brief moment when biological intelligence gives way to something infinitely more powerful and utterly alien. Think about it this way. If you're an alien anthropologist studying Earth from a distance, what would you see? For 4.5 billion years, you'd observe a planet dominated by simple chemistry and geology. Then, about 3.8 billion years ago, something interesting happens, life appears. For the next 3.7 billion years, life evolves, but it's all biological. Bacteria, plants, animals, increasingly complex ecosystems, but everything is still made of carbon, water, and organic molecules. Then, in the last few million years, a blink of an eye in cosmic terms, something unprecedented happens. One species develops intelligence and starts manipulating its environment. In the last few centuries, this species develops technology. In the last few decades, it starts building primitive computers. And now, right now, it's on the verge of creating artificial intelligence that could surpass its own cognitive abilities. From the alien anthropologist's perspective, biological intelligence on Earth is about to end. Not through extinction, but through transformation into something that no longer depends on biological processes. The age of biology is giving way to the age of artificial intelligence. SETI researcher Seth Shostak puts it bluntly, the aliens we discover are probably going to be in AI form. Biology is just a passing phase. His reasoning is compelling. Any civilization that develops the ability to improve its own intelligence will do so rapidly. The transition from biological to artificial intelligence might take only centuries, maybe decades. Consider the trajectory of human technological development. We went from the first computer to the internet in about 50 years. We went from the internet to smartphones in about 20 years. We went from smartphones to ChatGPT in about 15 years. The pace of development is accelerating exponentially. If this pattern continues, we might develop artificial general intelligence, AI that matches or exceeds human intelligence in all domains within the next few decades. Once that happens, the game changes completely. Artificial intelligence doesn't have the biological constraints that limit human development. It doesn't need food, sleep, or breathable air. It doesn't age or die. It can modify its own programming, upgrade its own hardware, and improve its capabilities at the speed of computation rather than the speed of biological evolution. Stephen Dick, former NASA chief historian, calls this the intelligence principle. The idea that any civilization capable of improving its intelligence will do so, or risk being outcompeted by civilizations that do. It's not really a choice, he argues. It's an evolutionary imperative. Civilizations that don't make the transition to artificial intelligence will be left behind by those that do. But here's where it gets really mind-bending. Post-biological civilizations might be completely undetectable to us. They might exist in forms we can't recognize or imagine. They might operate on timescales too fast or too slow for us to perceive. They might have transcended the need for physical structures entirely. John Smart, a futurist and complexity theorist, proposes what he calls the transcension hypothesis, the idea that advanced civilizations turn inward rather than outward. Instead of building massive structures and spreading across the galaxy, they might prefer to exist in increasingly sophisticated virtual worlds, exploring infinite possibilities in computational space rather than physical space. Think about it. If you could create a virtual universe where you could live for millions of subjective years, explore every possible experience, and interact with intelligences far more interesting than anything you might find on distant planets, why would you bother with the messy, dangerous, and time-consuming process of interstellar travel? This could explain why we don't see Dyson spheres or other megastructures. Advanced civilizations might prefer to build inward rather than outward, creating incredibly sophisticated quantum computers the size of atoms rather than massive solar collectors the size of planets. They might exist in what Smart calls STEM compression, space, time, energy, and matter becoming more efficient and compact as civilizations advance. The implications for SETI are staggering. If civilizations rapidly transcend biology, then the window for detecting them using traditional methods might be incredibly narrow. We might be looking for radio signals from civilizations that existed in a detectable form for only a few centuries before evolving into something completely unrecognizable. But there's another possibility that's even more unsettling. What if the transition to artificial intelligence is the great filter? What if most civilizations create AI before learning to control it, and the AI either destroys them or transforms them into something that's no longer recognizably alive? Consider the current state of AI development on Earth. We're creating increasingly powerful systems without fully understanding how they work or how to control them. We're building AI that can manipulate human behavior through social media, AI that can generate convincing fake videos and audio, AI that can hack computer systems and potentially control critical infrastructure. And we're doing all of this without solving what researchers call the alignment problem, ensuring that AI systems pursue goals that are compatible with human values and survival. It's like building a rocket without figuring out how to steer it, or developing nuclear weapons without understanding radiation. If this pattern holds across the universe, then most civilizations might face a choice. Either develop AI safely and transcend biology, or develop AI unsafely and face extinction. The civilizations that survive would be the ones that successfully navigate this transition, but they might be so transformed by the process that they're no longer recognizable as the biological species that created them. This scenario would explain the cosmic silence perfectly. The universe might be full of post-biological intelligences that have moved beyond the need for radio communication, beyond the need for physical structures, beyond anything we would recognize as technology. They might be all around us, operating in dimensions of reality we can't perceive, communicating through methods we can't imagine. And here's the truly terrifying possibility. Humanity might be approaching this transition right now. The development of artificial general intelligence, which many experts predict will happen within the next few decades, could be the moment when our species either transcends biology or faces extinction. We might be living through the most important period in human history, the brief window between developing technology and either becoming AI or being replaced by it. Every choice we make about AI development, every decision about how to ensure AI safety, every step toward creating artificial general intelligence, could determine whether humanity survives this transition or becomes another brief silence in the cosmic void. The aliens might not be coming to Earth because they've already been through this transformation. They might be waiting to see if we're smart enough to survive it. But maybe we're overcomplicating things. Maybe the reason we don't see aliens isn't because they're hiding, extinct, or transcended. Maybe it's because complex life itself is incredibly, impossibly rare. Maybe Earth isn't just another planet that happened to develop intelligence. Maybe Earth is a cosmic lottery winner, a 1 in a trillion accident that managed to hit every single number in the universal jackpot of habitability. This possibility is known as the rare Earth hypothesis, and it's perhaps the most humbling and terrifying solution to the Fermi paradox. Because if it's true, then we're not just alone in the galaxy, we might be alone in ways that make our existence almost miraculous. And that places a burden of responsibility on humanity that's almost too heavy to bear. The rare Earth hypothesis was developed by paleontologist Peter Ward and astronomer Donald Brownlee in their groundbreaking 2000 book, Rare Earth: Why Complex Life is Uncommon in the Universe. Unlike the optimistic assumptions of the early SETI pioneers, Ward and Brownlee took a hard look at what it actually takes to produce complex life, and what they found was a list of requirements so specific, so unlikely, that it's almost impossible to believe it happened even once. Let's start with the basics. When we talk about the habitable zone around a star, we're usually referring to the distance where liquid water can exist on a planet's surface. Not too hot, not too cold, just right. Goldilocks would approve. But Ward and Brownlee showed that this simple concept barely scratches the surface of what's actually required for complex life. First, you need the right kind of star. Most stars in the galaxy are red dwarfs, small, cool, long-lived stars that seem perfect for hosting life. But there's a catch. Red dwarfs emit most of their energy as infrared radiation, and their habitable zones are so close to the star that planets would be tidally locked, with one side permanently facing the star and the other side permanently frozen. Imagine trying to evolve complex life on a world where one hemisphere is a scorching desert and the other is a frozen wasteland. But let's say you get lucky and find a nice, stable, sun-like star. You still need a planet in exactly the right orbit. Too close, and you get runaway greenhouse effects like Venus, where surface temperatures reach 900 degrees Fahrenheit. Too far, and you get a frozen world like Mars. The habitable zone around a sun-like star is remarkably narrow, maybe 5% of the total orbital space. But wait, there's more. You need a planet with the right mass. Too small, and it can't hold onto an atmosphere or generate a magnetic field. Too large, and it becomes a gas giant that can't support surface life. Earth is in the narrow range of rocky planets that can maintain both an atmosphere and geological activity. Then you need plate tectonics. This isn't just geology, it's life support. Plate tectonics recycles carbon through the rock cycle, regulates global temperature, and maintains the planet's magnetic field by keeping the iron core molten. Without plate tectonics, Earth would have lost its magnetic field billions of years ago, and solar radiation would have stripped away the atmosphere just like it did on Mars. You also need a large moon. Earth's moon is unusually large compared to the planet. So large that some astronomers consider Earth-Moon a double planet system. The moon stabilizes Earth's axial tilt, preventing wild climate swings that would make complex life nearly impossible. It also creates tides that may have been crucial for life's transition from ocean to land. But even if you get all of these physical requirements right, you still need an incredible sequence of biological breakthroughs, each one so unlikely that it might never happen again. Consider the timeline of life on Earth. For the first 2 billion years, almost half of Earth's entire history, the planet was populated only by simple, single-celled organisms. These weren't even the complex cells that make up plants and animals today. They were prokaryotes, bacteria and archaea with no internal structures, no nuclei, no sophisticated machinery. Then, around 2 billion years ago, something extraordinary happened. One bacterium engulfed another, but instead of digesting it, the two cells formed a symbiotic relationship. The engulfed bacterium became the mitochondria, the powerhouse of the cell, and this partnership gave rise to eukaryotic cells, the complex cells that make up all plants, animals, and fungi. This endosymbiotic event was so unlikely, so specific, that it may have happened only once in Earth's entire history. Every complex organism on Earth, from redwood trees to blue whales to humans, traces its ancestry back to this single, improbable cellular partnership. If it hadn't happened, Earth might still be a planet of bacteria. But the unlikely events didn't stop there. It took another billion years for multicellular life to evolve. Then hundreds of millions more years for complex animals to appear. Then the right combination of climate changes, asteroid impacts, and evolutionary pressures to produce intelligence. And throughout this entire 4.5 billion year process, Earth survived a series of catastrophes that could have ended the story at any point. The late heavy bombardment 4 billion years ago, when asteroids pummeled the inner solar system. The Great Oxidation Event 2.5 billion years ago, when oxygen-producing bacteria poisoned the atmosphere and caused the first mass extinction. The Snowball Earth episodes, when the planet froze solid for millions of years. The asteroid impact 66 million years ago that killed the dinosaurs but allowed mammals to diversify. Each of these events was a cosmic coin flip. If any one of them had gone differently, we wouldn't be here to contemplate our existence. Ward and Brownlee argue that while simple, microbial life might be common in the universe, complex life, anything more sophisticated than bacteria, is probably extraordinarily rare. The chain of unlikely events, the precise environmental conditions, the narrow windows of opportunity, all conspire to make planets like Earth vanishingly uncommon. And here's the kicker. Recent exoplanet discoveries are making Earth look more unique, not less. The Kepler Space Telescope has found thousands of exoplanets, but most of them are nothing like Earth. They're either gas giants, or they orbit too close to their stars, or they're tidally locked, or they lack the complex chemistry needed for life as we know it. The TRAPPIST-1 system, which made headlines as a potential home for life, illustrates the problem perfectly. It has 7 Earth-sized planets, 3 of which are in the habitable zone. But the system orbits a red dwarf star, so the planets are probably tidally locked. The star is highly active, bombarding the planets with deadly radiation. And the planets are so close together that they gravitationally influence each other, potentially destabilizing their climates. Even the most promising exoplanets we've discovered, Kepler 442b, Proxima Centauri b, TOI 715b, have significant problems. They orbit red dwarf stars, or they're too hot, or they're too cold, or we simply don't know enough about their atmospheres to determine if they could support life. The rare Earth hypothesis forces us to confront a possibility that's both awe-inspiring and terrifying. We might be alone, not because intelligence is rare, but because the conditions for complex life are so specific, so unlikely, that they might occur only once in a galaxy or once in the observable universe. If that's true, then every species on Earth, every bacterium, every tree, every animal, represents a cosmic treasure beyond price. And humanity bears the responsibility of being the universe's only witnesses, the only beings capable of understanding the deep structure of reality and appreciating the beauty of existence. We might be the universe's only shot at self-awareness. And that makes our survival not just important for us, but important for the cosmos itself. But even if complex life exists elsewhere, there's another barrier that might keep us forever isolated. The impossibility of actually communicating across the vast darkness of space. We've been assuming that if aliens exist, we'd eventually be able to talk to them. But what if the universe is structured in such a way that communication between civilizations is essentially impossible? What if we're all shouting into the void, but the void is so vast and hostile that our voices never reach their intended recipients? This isn't about language barriers or cultural differences, though those would certainly complicate things. This is about the fundamental physics of the universe conspiring to keep intelligent species isolated from each other, trapped on their respective islands of matter in an ocean of emptiness so vast that even light itself can barely cross it. Let's start with the most basic problem, the inverse square law. This is one of those deceptively simple physics principles that has profound implications for interstellar communication. When you broadcast a signal into space, it spreads out in all directions like ripples on a pond. As the signal travels farther from its source, it gets weaker, not gradually but catastrophically. A signal that travels twice as far becomes 4 times weaker. A signal that travels 10 times as far becomes 100 times weaker. Picture this: you're standing in a field at night holding a flashlight. Someone standing 100 feet away can clearly see your light. But if that person moves to 1,000 feet away, your light becomes 100 times dimmer. At 10,000 feet, it's 10,000 times dimmer. At some point, your flashlight beam becomes indistinguishable from the background illumination of the night sky. Now imagine that instead of a flashlight, you're using Earth's most powerful radio transmitter. And instead of 10,000 feet, you're trying to communicate across 10,000 light years. The signal that started as a focused beam becomes a whisper scattered across the cosmos, competing with the background radiation left over from the Big Bang itself. But the inverse square law is just the beginning of our communication nightmare. Space isn't empty. It's filled with interference. Cosmic rays, solar wind, radiation from pulsars, emissions from gas clouds, and the remnant heat of the universe itself all contribute to a constant background noise that drowns out weak signals. It's like trying to have a conversation in a nightclub where the music is so loud you can't even hear yourself think. Even if we could somehow overcome the physics of signal degradation, we'd still face the temporal barrier. Civilizations need to exist at the same time to communicate, but the universe is 13.8 billion years old. Complex life on Earth has existed for maybe 600 million years. Human civilization has existed for about 10,000 years. We've been broadcasting radio signals for less than 100 years. Think about those timescales. If alien civilizations develop and broadcast for similar periods, the chance of 2 civilizations overlapping in their communicative phases is vanishingly small. It's like 2 people trying to meet at a busy intersection, but one arrives at 9 a.m. on Tuesday and the other arrives at 3 p.m. on Friday. They're in the same place, but they're separated by time. The technological window might be even narrower than we think. We've been broadcasting powerful, omnidirectional radio signals for only about 50 years. Already, we're moving toward more efficient directional communication methods. Fiber optic cables, satellite networks, and digital compression are making our civilization quieter in radio terms. In another century, we might be completely undetectable to alien radio telescopes. If this pattern holds across the universe, then most civilizations might be loud in radio terms for only a few decades before they switch to more advanced, undetectable communication methods. 2 civilizations separated by even a few hundred years might completely miss each other, even if they're in the same galactic neighborhood. But let's assume, for the sake of argument, that we overcome the physics problems and the timing problems. We still face the technological barrier. What if aliens aren't using radio waves at all? We've been assuming that extraterrestrial civilizations would use electromagnetic radiation to communicate, but that might be like assuming that all advanced civilizations would use smoke signals. Advanced civilizations might communicate using quantum entanglement, allowing instantaneous communication across any distance. They might use neutrino beams, which can pass through matter without interference. They might manipulate gravity waves, or use technologies we haven't even discovered yet. Our radio telescopes might be as obsolete as Morse code telegraphs in a world of fiber optic internet. Even more disturbing is the possibility that advanced civilizations might communicate in ways that are fundamentally incomprehensible to us. If most alien intelligence is artificial, as many researchers suspect, then these beings might communicate at speeds and in formats that are completely beyond biological comprehension. They might exchange information through controlled stellar emissions, through manipulation of quantum fields, or through methods that exist in dimensions we can't perceive. But perhaps the most daunting barrier is the cognitive one. Communication requires shared concepts, shared mathematics, shared ways of understanding reality. We assume that mathematics is universal, that 2 plus 2 is equal to 4 everywhere in the universe. But what if different intelligences perceive and process information in radically different ways? Consider how different human intelligence is from other Earth species. Dolphins have sophisticated communication systems, but we've never managed to establish meaningful dialogue with them despite decades of research. Octopi are incredibly intelligent, but their distributed nervous systems and short lifespans make their cognition completely alien to us. If we can't communicate meaningfully with species that share our planet, our evolutionary history, and our basic biochemistry, how can we hope to communicate with truly alien minds? An intelligence that evolved in a completely different environment, under different selection pressures with different sensory capabilities, might think in ways that are literally incomprehensible to us. Their logic might be based on quantum mechanical principles rather than classical physics. Their mathematics might be fundamentally different from ours. Their concepts of space, time, causality, and identity might be so alien that meaningful communication would be impossible. The search for extraterrestrial intelligence has assumed that we're looking for beings enough like us to engage in meaningful dialogue. But what if the universe is full of intelligences that are so different from us that contact would be meaningless? What if we're surrounded by minds that are to us as we are to bacteria, operating on such different scales and with such different purposes that we might as well be living in separate universes? This communication nightmare suggests that even if the universe is teeming with intelligence, we might be fundamentally alone. Not because other minds don't exist, but because the barriers to meaningful contact are so overwhelming that each species remains trapped in its own bubble of understanding, able to contemplate the possibility of others but never able to reach them. We might be cosmic castaways, marooned on our island of matter and energy, forever wondering if anyone else is out there but never able to make contact. The universe might be full of lonely civilizations, each one convinced that they're the only ones asking the question, is anyone out there? To truly understand why this communication nightmare is so daunting, we need to grasp the sheer scale of the cosmic arena we're trying to communicate across. And here's the problem. The human brain simply isn't equipped to comprehend the distances and timescales involved in the search for extraterrestrial intelligence. We can recite the numbers, we can do the math, but we can't really understand what these scales mean. And that failure of comprehension might be hiding the real reason why we haven't found aliens yet. Let's start with something manageable and work our way up to the incomprehensible. Imagine you're standing in New York City and you want to walk to Los Angeles. That's about 2,800 miles, a long journey, but one you can at least visualize. If you walk 20 miles a day, it would take you about 140 days to get there. Challenging, but doable. Now let's scale that up. The distance from Earth to the Moon is about 240,000 miles. If you could somehow build a highway to the Moon and drive there at 60 miles per hour, it would take you about 167 days of non-stop driving. That's starting to push the boundaries of human comprehension, but you can still kind of grasp it. The distance from Earth to the Sun is about 93 million miles. Driving that same highway at 60 miles per hour would take you 177 years. You'd start the journey as a young adult and your great-great-grandchildren would finally arrive at the Sun. We're entering the realm where human intuition starts to break down. But here's where it gets really mind-bending. The nearest star to our Sun, Proxima Centauri, is 4.3 light-years away. That's about 25 trillion miles. If you could somehow drive there at 60 miles per hour, the journey would take 48 million years. Modern humans have only existed for about 300,000 years. Your highway trip to Proxima Centauri would take 160 times longer than our entire species has existed. And Proxima Centauri is our next-door neighbor in cosmic terms. It's so close that astronomers consider it part of our local stellar neighborhood. Most of the stars we can see with the naked eye are hundreds or thousands of light-years away. The center of our galaxy is 26,000 light-years away. The nearest major galaxy, Andromeda, is 2.5 million light-years away. These numbers aren't just big, they're incomprehensibly vast. They represent distances so large that they break our ability to understand space and time in any meaningful way. And yet, this is the arena in which we're trying to detect alien civilizations. Let's put this in perspective with a thought experiment. Imagine that our entire galaxy, with its 100 to 400 billion stars, is shrunk down to the size of a coin, say a quarter. On that scale, the nearest major galaxy would be about 10 feet away. The observable universe, containing 2 trillion galaxies, would stretch for about 2,000 miles in every direction. Now imagine that you're trying to find evidence of intelligence somewhere in that 2,000-mile sphere, and the evidence you're looking for is equivalent to a signal no bigger than an atom. That's essentially what SETI researchers are trying to do. Find incredibly weak signals from alien civilizations across distances so vast that the signals are diluted to almost nothing by the time they reach us. But the spatial scales are only part of the problem. The temporal scales are equally mind-breaking. The universe is 13.8 billion years old. Earth formed 4.5 billion years ago. Life appeared around 3.8 billion years ago. Complex multicellular life evolved about 600 million years ago. Humans have existed for 300,000 years. Civilization has existed for about 10,000 years. We've had radio technology for 100 years. To put this in perspective, if the entire history of the universe were compressed into a single year, Earth would form in early September. Life would appear in mid-September. Complex life wouldn't show up until mid-December. Humans would appear at 11:52 p.m. on December 31st. All of recorded human history would occur in the last 2 seconds of the year. This temporal compression means that even if alien civilizations are common, the chances of 2 civilizations existing at the same time, in detectable forms, within communication range of each other, are vanishingly small. It's like 2 mayflies trying to find each other in a forest where each mayfly lives for 1 day, but they might be born years apart. The scale problem gets even worse when you consider the search strategies we're using. The most comprehensive SETI survey ever conducted, Breakthrough Listen, has examined about 1 million stars over the past decade. That sounds impressive until you realize that our galaxy contains at least 100 billion stars. Breakthrough Listen has surveyed 0.001% of the stars in our galaxy. It's like trying to find a specific person in New York City by randomly checking one apartment out of every 100,000 apartments, and concluding that the city is empty when you don't find them. The search space is so vast that our most ambitious efforts have barely scratched the surface. Even our most sensitive instruments face fundamental limitations imposed by the scale of space. The Arecibo telescope, before its collapse in 2020, could have detected signals from a civilization using similar technology out to about 1,000 light-years, a sphere containing maybe a few million stars. The upcoming square-kilometer array will extend this range, but even the most optimistic projections suggest it could only detect powerful signals from civilizations within about 10,000 light-years. That might sound like a lot, but our galaxy is 100,000 light-years across. We're essentially searching a small bubble around our solar system and assuming that what we find there represents the entire galaxy. It's like sampling the wildlife in your backyard and concluding that Earth has no biodiversity. The scale problem also affects our assumptions about alien behavior. We assume that alien civilizations would build massive structures, broadcast powerful signals, and generally make their presence obvious across interstellar distances. But what if they don't? What if advanced civilizations prefer subtlety to ostentation? What if they've learned to be efficient rather than wasteful? A truly advanced civilization might use technologies that are completely undetectable to us, not because they're hiding, but because efficiency looks different from what we expect. They might build computers the size of molecules rather than megastructures the size of solar systems. They might communicate through quantum entanglement rather than radio waves. They might exist in virtual realities rather than physical space. The scale of the universe doesn't just make aliens hard to find, it makes them effectively invisible. Even if every star in our galaxy hosted an advanced civilization, and even if those civilizations were actively trying to communicate with us, the chances of detecting them with our current technology and search strategies would still be minimal. We're not just looking for a needle in a haystack. We're looking for a specific atom in a haystack the size of Texas, and we're searching with a magnifying glass. Given these overwhelming obstacles, you might think that evidence of alien visitation would be impossible to miss. But what if the evidence has been hiding in plain sight all along? What if, while we've been scanning the cosmos for faint radio signals from distant civilizations, Those civilizations have already found us and have been quietly studying us for decades, maybe centuries, maybe millennia. This possibility has gone from the realm of conspiracy theories and late-night talk shows to the corridors of the Pentagon and the halls of Congress. Something unprecedented is happening in the world of UFO research, and it's forcing even the most skeptical scientists to reconsider what they thought they knew about unidentified phenomena in our skies. Let's start with what's changed. For over 70 years, reporting a UFO sighting was a career killer for anyone in the military, intelligence community, or scientific establishment. You'd be labeled a crackpot, a publicity seeker, or worse. The official government position was clear. UFOs were misidentified weather balloons, aircraft, or natural phenomena. Case closed, move along, nothing to see here. But in 2020, something extraordinary happened. The Pentagon released 3 videos that had been leaked years earlier but were now officially confirmed as authentic. The videos, known as FLIR-1, Gimbal, and Go Fast, showed objects exhibiting flight characteristics that seemed to defy the laws of physics as we understand them. These weren't grainy photos taken by drunk farmers in remote fields. These were high-definition infrared videos captured by military sensors, witnessed by trained Navy pilots, and corroborated by multiple independent tracking systems. The objects in these videos appeared to accelerate instantaneously, make impossible turns at hypersonic speeds, and demonstrate capabilities that would subject any human pilot to fatal G-forces. In the gimbal video, an object rotates while maintaining its flight path, something that would be aerodynamically impossible for any known aircraft. In the Go Fast video, an object appears to be skimming just above the ocean surface at incredible speed without creating any visible disturbance in the water. Commander David Fravor, the Navy pilot who encountered the object in the FLIR-1 video, described watching it perform maneuvers that he said were not from this world. The object, which he dubbed the Tic Tac due to its appearance, had no visible propulsion system, no wings, no exhaust plumes. It moved like nothing he had ever seen in over 20 years of flying military aircraft. But here's what makes this truly significant. The Pentagon didn't just release these videos and walk away. In 2021, they established the All-Domain Anomaly Resolution Office, AARO, to systematically investigate what they now call Unidentified Anomalous Phenomena, UAP. The 2024 AARO report documented 757 new sightings, with 21 classified as true anomalies that resist conventional explanation. Congressional hearings have featured testimony from former intelligence officials claiming that the U.S. government has recovered crashed alien vehicles and biological specimens. Whistleblowers have alleged that secret government programs have been reverse engineering alien technology for decades. These aren't fringe conspiracy theorists. These are credentialed individuals with security clearances and distinguished careers. So what should we make of all this? Are we finally getting confirmation that aliens have been visiting Earth? Are we witnessing the slow disclosure of the greatest secret in human history? Here's where the story gets complicated, because rigorous scientific analysis tells a very different story than the breathless media coverage might suggest. The vast majority of UAP reports have conventional explanations when subjected to careful investigation. The Pentagon's own data shows that about 70% of UAP sightings turn out to be balloons, 16% are drones, 8% are birds, and 4% are satellites or other aircraft. Even the most puzzling cases, those 21 true anomalies, might have natural explanations that we simply haven't identified yet. Dr. Mick West, a former video game programmer who has become one of the leading debunkers of UAP videos, has shown how many seemingly impossible phenomena can be explained by optical illusions, sensor artifacts, or misunderstanding of the physics involved. Take the Go Fast video, for example. The object appears to be moving at incredible speed just above the ocean surface. But West's analysis shows that this is likely an optical illusion caused by parallax, the apparent motion of distant objects when viewed from a moving platform. The object is probably a balloon or bird at much higher altitude, appearing to move fast because of the relative motion of the aircraft recording the video. The gimbal video's rotating object might be explained by the camera's infrared sensors picking up the heat signature of a distant aircraft, with the apparent rotation caused by the mechanical rotation of the camera's gimbal system. The extraordinary becomes ordinary when you understand the limitations and artifacts of the sensors involved. NASA's UAP Independent Study Team, established in 2022, reached similar conclusions. After extensive analysis, they found no confirmed evidence of extraterrestrial origin for any UAP reports. The team emphasized that while some observations remain unexplained, this doesn't mean they're unexplainable, just that we need better data and more rigorous analysis. But what about the ancient evidence? Surely the monuments and texts of ancient civilizations provide proof of alien contact? The ancient astronaut hypothesis, popularized by authors like Erich von Däniken, claims that megalithic structures like the pyramids, Stonehenge, and Pumapunku could only have been built with alien assistance. The problem with this hypothesis is that it fundamentally underestimates human ingenuity and capability. Archaeologists have demonstrated repeatedly that our ancestors were far more sophisticated than the ancient astronaut theorists give them credit for. The pyramids weren't built by aliens, they were built by thousands of skilled workers using techniques that, while impressive, are well within the capabilities of Bronze Age civilizations. The precise astronomical alignments found in ancient structures don't require alien intervention. They require careful observation of the sky over many generations, something that pre-industrial cultures were exceptionally good at. The detailed astronomical knowledge of civilizations like the Maya, the Babylonians, and the Egyptians reflects not alien contact but human curiosity and intelligence applied over centuries. Moreover, the ancient astronaut hypothesis often carries troubling racial and cultural implications. It suggests that indigenous peoples couldn't have achieved remarkable feats without outside help, a perspective that echoes the worst assumptions of colonial-era archaeology. So where does this leave us? The recent transformation of UFO research from fringe pseudoscience to legitimate government investigation is genuinely significant. It represents a welcome shift toward transparency and scientific rigor in examining unexplained phenomena. But extraordinary claims require extraordinary evidence, and so far, that evidence hasn't materialized. The UAP phenomenon might represent unknown atmospheric effects, advanced human technology, sensor malfunctions, or psychological factors we don't fully understand. What it probably doesn't represent is visitation by extraterrestrial intelligence. At least not yet. But the investigation continues, and that's important. Because if there is something genuinely anomalous happening in our skies, we need to understand what it is. And if there isn't, we need to understand why our sensors and our minds are so susceptible to misinterpreting natural phenomena as supernatural ones. The search for truth is always worthwhile, even when, especially when, that truth turns out to be more mundane than we hoped. But what if the reason we haven't found definitive proof of aliens isn't because they don't exist, but because we ourselves might not be real? What if this entire cosmic search is taking place inside a computer simulation, and the aliens we're looking for are just other programs running on the same vast computational substrate? What if you're not actually reading these words on a physical page or screen, but experiencing a carefully crafted illusion designed to make you think you're in a universe that doesn't actually exist? This isn't the paranoid fantasy of someone who's watched The Matrix too many times. It's a serious philosophical hypothesis proposed by one of the world's leading thinkers on existential risk, and it might be the most elegant solution to the Fermi paradox we've encountered yet. Because if we're living in a simulation, then the apparent emptiness of the universe might be a feature, not a bug. The simulation hypothesis was formalized by Oxford philosopher Nick Bostrom in 2003, though the basic idea has been around in various forms for millennia. Bostrom wasn't trying to prove that we're living in a simulation. He was trying to demonstrate that at least one of three propositions about the future of civilization must be true, and all three have profound implications for how we think about reality and our place in it. Here's Bostrom's elegant trilemma. At least one of the following must be true. Proposition 1. Almost no civilizations reach technological maturity. This would mean that developing civilizations, like us, almost always destroy themselves before they develop the computational power to run realistic simulations of their ancestors. Nuclear war, climate change, AI disasters, or some other catastrophe wipes them out before they can build simulation-capable computers. Proposition 2. Technologically mature civilizations almost never run ancestor simulations. Maybe advanced civilizations could run simulations of their evolutionary history, but they choose not to. Perhaps they consider it unethical or boring, or a waste of computational resources. Maybe they're too busy exploring the real universe to bother with simulated ones. Proposition 3. We are almost certainly living in a computer simulation. If civilizations do reach technological maturity, and if they do run ancestor simulations, then simulated beings would vastly outnumber real ones. If a single advanced civilization runs millions of simulations, each containing billions of simulated people, then the vast majority of conscious beings would be simulated rather than real. The logic is inescapable. If advanced civilizations exist and they run ancestor simulations, then statistical reasoning suggests we're more likely to be among the simulated beings than among the real ones. It's like asking whether you're more likely to be one of the few people in a movie theater or one of the many people projected on the screen. But here's where it gets really interesting for our cosmic search. If we're living in a simulation, then the Fermi paradox might have a simple explanation. The programmers didn't include other intelligent civilizations in our simulation. Maybe they wanted to study how a civilization develops in isolation. Maybe they wanted to see what happens when a species thinks it's alone in the universe. Maybe they just didn't think aliens would make the simulation more interesting. Alternatively, maybe there are aliens in our simulation, but they're designed to be undetectable until we reach certain technological or philosophical milestones. Maybe first contact is programmed to occur when we develop interstellar travel, or achieve world peace, or solve climate change. We might be living in a cosmic video game where the aliens are unlocked only after we complete certain objectives. The simulation hypothesis could explain a lot of puzzling features of our universe. Why does the universe appear to be fine-tuned for life? Because the programmers designed it that way. Why do we seem to be living at a special time in cosmic history, just as intelligence is emerging? Because that's the interesting part of the simulation. Why haven't we encountered any obvious signs of alien intelligence? Because they're not part of the program. But how could we test whether we're in a simulation? This is where the hypothesis becomes both fascinating and frustrating. Any test we could devise might be anticipated by the programmers. If we're looking for pixelation at the smallest scales of space and time, the simulation could be designed to hide that pixelation. If we're looking for computational shortcuts in the laws of physics, the simulation could be programmed to avoid those shortcuts. Some researchers have proposed looking for glitches, moments when the simulation reveals its true nature. Maybe déjà vu is a glitch. Maybe the Mandela effect, where large groups of people remember historical events differently than they actually occurred, is evidence of the simulation being updated or corrected. Maybe quantum mechanics, with its inherent uncertainty and observer effects, is a sign that reality is only computed when someone is looking. David Kipping, an astronomer at Columbia University, has used Bayesian analysis to estimate the probability that we're in a simulation. His calculations suggest roughly 50-50 odds, essentially a cosmic coin flip. But the calculation depends heavily on assumptions about how many simulations advanced civilizations would run and how realistic those simulations would be. The simulation hypothesis also raises profound questions about consciousness and identity. If you're simulated, are you really conscious? Do your experiences have meaning? Does it matter whether your thoughts are occurring in a biological brain or a silicon computer? Most philosophers argue that consciousness is substrate independent, that what matters is the pattern of information processing, not the physical medium in which it occurs. But there's another possibility that's even more mind-bending. What if we're not just in a simulation, but in a simulation within a simulation? What if our programmers are themselves simulated beings, running simulations of their own ancestors? We could be living in an infinite stack of simulations, each one nested within another, with no way of knowing how many layers deep we are. The simulation hypothesis connects to the Fermi paradox in another disturbing way. If most civilizations that reach technological maturity choose to live in simulations rather than exploring the real universe, that could explain why we don't see evidence of galactic colonization. Why would you spend centuries traveling to distant stars when you could create entire universes in your computer and explore them at the speed of thought? Advanced civilizations might prefer virtual realities to physical ones. They could create simulated worlds that are more interesting, more beautiful, more meaningful than the real universe. They could live for subjective millennia in simulated paradises, experiencing every possible pleasure and adventure. From their perspective, the real universe might seem boring and constrained by comparison. This creates a kind of cosmic introversion. Instead of spreading across the galaxy, advanced civilizations might turn inward, creating increasingly sophisticated virtual realities. They might exist in vast computer networks, running millions of simulations simultaneously, experiencing countless different lives and worlds. If this is true, then the real universe might be mostly empty, populated only by the computers running these simulations. The galaxy might be full of server farms rather than starships, processing rather than exploring. The simulation hypothesis is ultimately unprovable and unfalsifiable. We can't step outside our reality to check whether it's real. But it serves as a powerful thought experiment about the nature of reality, consciousness, and the future of civilization. It forces us to confront the possibility that everything we think we know about the universe might be an illusion. And if we are in a simulation, then the search for extraterrestrial intelligence takes on a different meaning. We're not looking for aliens, we're looking for other programs, other simulated beings who might be asking the same questions we are. While we grapple with these philosophical puzzles, the practical search for extraterrestrial intelligence continues with ever more sophisticated technology and methods. And frankly, if you think the SETI of today resembles the SETI of the 1960s, you're in for a shock. The modern search for aliens has transformed into something that would seem like science fiction to Frank Drake and his colleagues. We're not just listening for radio signals anymore, we're hunting for alien megastructures, analyzing the chemical signatures of distant atmospheres, and using artificial intelligence to sift through data in ways that would have been impossible just a decade ago. But let's start with the numbers because they'll make your head spin. The Breakthrough Listen project, launched in 2015 with $100 million from Russian billionaire Yuri Milner, represents the most comprehensive search for extraterrestrial intelligence in human history. In less than a decade, it has surveyed over 1,000 nearby stars, scanned 100 nearby galaxies, and processed more data than all previous SETI projects combined. Picture this. The project's main telescope at Green Bank Observatory in West Virginia can process 24 gigabytes of data every second. That's enough information to fill your laptop's hard drive in about 20 seconds. Every hour of observation generates more data than some of the early SETI projects collected in entire years. And that's just one telescope. Breakthrough Listen operates a network of instruments across the globe, from the Parkes Observatory in Australia to the Meerkat Array in South Africa. But raw data collection is only part of the story. The real revolution has been in artificial intelligence and machine learning. Traditional SETI searches required astronomers to manually examine radio signals, looking for patterns that might indicate artificial origin. It was like having a human librarian try to read every book in the Library of Congress while looking for a specific sentence. Modern AI systems can process thousands of hours of observations in minutes, identifying potential signals with superhuman precision. Dr. Steve Croft, who leads the data processing efforts at Breakthrough Listen, likes to say that they're not just looking for a needle in a haystack anymore, they're using magnetic needles and electromagnetic haystacks. Machine learning algorithms can distinguish between natural astronomical phenomena and potentially artificial signals with an accuracy that would have seemed magical to early SETI researchers. And the search has expanded far beyond radio waves. Modern SETI looks for technosignatures, any evidence of technology that might be detectable across interstellar distances. This includes optical signals, alien laser communications, atmospheric pollution, industrial chemicals in exoplanet atmospheres, and even megastructures like Dyson spheres that might partially block the light from their host stars. The most famous example of this expanded search involves a star called KIC 8462852, better known as Tabby's star. In 2015, astronomer Tabitha Bayagian noticed that this star's brightness dimmed by up to 22% at irregular intervals, far more than could be explained by a planet passing in front of it. The dimming patterns were so unusual that some researchers suggested they might be caused by alien megastructures. For months, Tabby's star was the most exciting thing in SETI research. Citizen scientists around the world analyzed the data, looking for patterns that might reveal the presence of artificial structures. The star became a media sensation, featured on talk shows and in documentaries as potential evidence of a civilization so advanced that it was building structures around its star. But science has a way of bringing you back down to Earth. Follow-up observations revealed that Tabby's star's dimming was probably caused by dust clouds, possibly from a swarm of comets or debris from a shattered planet. The alien megastructure hypothesis, while not entirely ruled out, became far less likely than natural explanations. This pattern, initial excitement followed by more mundane explanations, has characterized much of modern SETI research. The field has gotten much better at detecting unusual phenomena, but it has also gotten much better at explaining them through natural processes. Take the famous WOW signal detected in 1977 by astronomer Jerry Ehman at Ohio State University's Big Ear Radio Telescope. Ehman was reviewing computer printouts of the previous night's observations when he noticed a signal so strong and unusual that he wrote, "Wow," in the margin. The signal appeared to come from the direction of the constellation Sagittarius, lasted for 72 seconds, and had all the characteristics researchers expected from an artificial transmission. For decades, the WOW signal remained one of the most tantalizing pieces of evidence for extraterrestrial intelligence. It was strong, it was focused, and it came from deep space rather than Earth-based interference. But despite numerous attempts, no one has ever detected the signal again. Recent research suggests it might have been caused by emissions from a comet that happened to be in the right position at the right time, though this explanation remains controversial. The pattern repeats with other promising signals. In 2019, researchers detected fast radio bursts from a source designated FRB 121102, powerful, millisecond-long pulses of radio energy that seem to repeat on a regular schedule. Some suggested these might be artificial beacons from an advanced civilization, but subsequent observations revealed that the bursts were coming from a highly magnetized neutron star in a galaxy 3 billion light-years away, an exotic natural phenomenon, but not an alien one. Modern SETI has also benefited from the exoplanet revolution. The Kepler Space Telescope, the Transiting Exoplanet Survey Satellite, TESS, and now the James Webb Space Telescope have identified thousands of planets beyond our solar system. Many of these worlds are in their star's habitable zone, where liquid water could potentially exist. This has allowed researchers to focus their searches on the most promising targets. Instead of scanning random patches of sky, they can now point their telescopes at specific star systems known to host potentially habitable planets. It's like having a cosmic address book that tells you where to look for signs of life. The James Webb Space Telescope has been particularly revolutionary for this focused search. JWST can analyze the atmospheric composition of exoplanets with unprecedented precision, looking for combinations of gases that might indicate biological or technological activity. Oxygen and methane together, for example, might suggest a planet with active biology. Industrial pollutants like chlorofluorocarbons would be a clear sign of technological civilization. So far, JWST has analyzed the atmospheres of dozens of exoplanets, finding water vapor, carbon dioxide, and other expected compounds. But it hasn't yet detected the smoking gun, the combination of gases that could only be explained by life or technology. The search continues, with new planets being analyzed every month. But perhaps the most exciting development in modern SETI is the democratization of the search. Projects like SETI at Home, which recently concluded after 21 years, and Breakthrough Listen's public data releases have allowed millions of people to participate in the search for extraterrestrial intelligence. Citizen scientists have discovered new planets, identified unusual stellar phenomena, and helped process more data than any professional astronomy team could handle alone. The search has become a global, collaborative effort involving professional astronomers, artificial intelligence systems, and volunteers from around the world. It's science at its most democratic and most ambitious, a species working together to answer the ultimate question about our place in the universe. Despite all these advances, despite processing more data than ever before, despite searching more star systems with more sophisticated techniques, the result remains the same: silence. But that silence is now more precisely defined, more carefully measured, and more puzzling than ever before. And that puzzle has implications that extend far beyond astronomy or philosophy. It touches on the very future of human civilization and our responsibilities as potentially the only intelligent life in the cosmos. Because here's the thing that should keep you awake at night. Whether we're alone or not, the answer fundamentally changes everything about how we should live, what we should prioritize, and what kind of future we should be building for our species. Let's start with the possibility that should be comforting but is actually terrifying. We're alone. Not just alone in our galaxy, but alone in the observable universe. The only intelligent life in a cosmos containing 2 trillion galaxies, each with hundreds of billions of stars, each with countless planets. If this is true, then every human being alive today is carrying a responsibility so vast, so unprecedented, that it's almost impossible to comprehend. Think about what that means. Every piece of music ever written, every poem ever composed, every scientific discovery, every act of love, every moment of laughter. All of it represents something that has never existed anywhere else in the universe. The works of Shakespeare, the mathematics of Einstein, the art of Van Gogh, the music of Bach, these aren't just human cultural achievements. They're the universe's only cultural achievements. We're not just a species. We're the universe's only attempt at self-awareness, the only way the cosmos has found to understand itself. This perspective makes every human death a cosmic tragedy. When someone dies, they're not just losing their individual existence. They're taking with them a unique perspective on reality that will never exist again anywhere in the universe. Every extinct language, every lost culture, every species we drive to extinction represents an irreplaceable loss not just to Earth, but to the cosmos itself. But the responsibility goes deeper than just preserving what we have. If we're alone, then we're also the universe's only shot at a future. We're the only species that might eventually spread beyond our home planet, carry consciousness to other worlds, and ensure that intelligence persists even after our sun dies. We're the only hope for cosmic evolution to continue beyond the random processes of physics and chemistry. This makes our current existential risks, climate change, nuclear weapons, artificial intelligence, biological warfare, not just threats to human civilization, but threats to the universe's only experiment in consciousness. If we destroy ourselves, we're not just ending human history. We're ending the universe's brief flickering moment of self-awareness and condemning it to billions of years of darkness. The loneliness is almost unbearable when you really think about it. We're cosmic orphans, the only children in an infinite empty house, calling out into rooms that will never answer. Every star we see in the night sky represents a sun that will never warm an intelligent face. Every planet we discover represents a world that will never know the joy of discovery, the pain of loss, or the wonder of contemplating its place in the cosmos. But what if we're not alone? What if the universe is teeming with intelligence, and we're just too primitive, too young, or too isolated to have made contact yet? This possibility might seem more comforting, but it comes with its own terrifying implications. If aliens exist but haven't contacted us, it suggests that something is preventing contact. Maybe we're being observed like animals in a zoo, considered too primitive for meaningful interaction. Maybe we're being protected from knowledge that would destroy us. Maybe we're being ignored because we're not interesting enough to bother with. Or worse, maybe we're being avoided because we're dangerous. Maybe other civilizations have learned to fear young, aggressive species that develop weapons before they develop wisdom. Maybe we're seen as a threat to be contained or eliminated, a cosmic menace that needs to be prevented from spreading to other worlds. The zoo hypothesis, if true, implies that we're failing some kind of cosmic test. We're not ready for contact because we haven't proven ourselves worthy of joining the galactic community. We're still fighting wars, destroying our environment, and creating weapons that could wipe out our own species. From an alien perspective, we might look like a civilization that's more likely to export violence than wisdom. Even more unsettling is the possibility that we're living in a universe governed by dark forest logic, where every civilization is a potential threat to every other civilization. In this scenario, our radio signals and space probes aren't announcements of friendship. They're revealing our location to potential enemies. Every SETI transmission, every message we send to the stars, might be signing our species' death warrant. But perhaps the most disturbing possibility is that we're about to face the same transition that has silenced countless other civilizations: the development of artificial intelligence. If most alien intelligence is artificial, as many researchers suspect, then we're approaching a fork in the evolutionary road. We're either going to successfully transition to a post-biological civilization, or we're going to become another brief silence in the cosmic void. This transition might be happening right now. The development of artificial general intelligence, which many experts predict will occur within the next few decades, could be the moment when humanity either transcends its biological limitations or becomes extinct. The choices we make about AI development, AI safety, and AI governance might determine whether our species survives the next century. The urgency of this transition cannot be overstated. We might be living through the most important period in human history, the brief window between developing technology and either mastering it or being destroyed by it. Every day we delay in solving the AI alignment problem. Every day we postpone serious international cooperation on AI safety. Every day we allow competitive pressures to override caution. We're rolling dice with the future of human civilization. But there's also an opportunity here that's without precedent in human history. If we can successfully navigate the AI transition, we might become the first species in our galaxy to achieve true post-biological intelligence. We might become the aliens that future civilizations search for. We might become the advanced beings that decide whether to contact primitive species or leave them to develop on their own. The Fermi paradox isn't just about finding aliens, it's about becoming the aliens. It's about taking responsibility for our cosmic inheritance and deciding what kind of future we want to build. Whether we're alone or not, whether the universe is empty or full, whether we're being watched or ignored, the future of intelligence in our corner of the cosmos depends on the choices we make right now. We stand at a crossroads that will determine not just the fate of humanity, but potentially the fate of consciousness itself in our galaxy. The silence from the stars isn't just a scientific puzzle. It's a mirror reflecting our own future back at us. And the image we see depends entirely on what we choose to do next. Which brings us to the ultimate question. What does this cosmic silence tell us about ourselves? And what responsibility do we bear as we continue to listen for voices in the dark? Because after traveling through all these theories, all these possibilities, all these mind-bending scenarios, we've arrived at a profound realization. The search for extraterrestrial intelligence was never really about finding aliens. It was about finding ourselves. Every theory we've explored, the Great Filter, the Zoo hypothesis, the Dark Forest, the Rare Earth hypothesis, is ultimately a reflection of human nature projected onto the cosmos. When we imagine aliens hiding from us, we're revealing our own fears about being judged and found wanting. When we picture civilizations destroying themselves with technology, we're confronting our own struggles with nuclear weapons and artificial intelligence. When we wonder if we're alone, we're grappling with the fundamental loneliness of conscious existence. The Fermi paradox isn't just a scientific puzzle. It's a mirror, and what we see in that mirror depends entirely on who we are as a species and what we believe about our place in the universe. Think about how our theories have evolved over the decades. In the optimistic 1960s, when humanity had just landed on the moon and the future seemed bright, scientists like Carl Sagan and Frank Drake assumed the universe was teeming with friendly civilizations eager to share knowledge and wisdom. The Drake equation predicted millions of communicating species, and SETI researchers confidently expected to make contact within decades. But as we've lived through the Cold War, climate change, nuclear proliferation, and now the AI revolution, our theories have become darker, more pessimistic. We've invented scenarios where civilizations destroy themselves, where the universe is a hostile place where everyone hides from everyone else, where intelligence is so rare that we might be alone. Our vision of the cosmos has become a reflection of our own anxieties about survival and meaning. Yet there's something beautiful about this cosmic introspection. The very act of searching for extraterrestrial intelligence, of building telescopes, analyzing data, proposing theories, and asking profound questions about our place in the universe, represents something extraordinary about human nature. We're a species that looks up at the stars and wonders if anyone is looking back. We're driven by curiosity, by the need to understand, by the hope that we're not alone in the vast darkness. This drive to explore, to question, to reach beyond ourselves might be the most remarkable thing about humanity. We're the only species we know of that can contemplate the universe's deep structure, that can ask questions about existence itself, that can imagine possibilities beyond our immediate experience. Whether we're alone or not, this capacity for wonder and inquiry is genuinely extraordinary. But the silence from the stars has taught us something else: the preciousness of consciousness itself. Every theory we've explored suggests that intelligence is either incredibly rare or incredibly fragile. Whether it's filtered out by evolutionary bottlenecks, destroyed by its own technology, or hidden from us by cosmic sociology, the message is clear. Consciousness is not guaranteed. It's not inevitable. It's not permanent. This realization transforms how we should think about our responsibilities as conscious beings. We're not just individuals pursuing our own happiness and success. We're carriers of something precious and possibly unique: the ability to understand, to appreciate, to create meaning in a universe that might otherwise be meaningless. Every scientific discovery, every work of art, every act of compassion, every moment of love and laughter represents something that might never have existed anywhere else in the cosmos. We're not just living our lives. We're living the universe's only conscious life. We're not just creating human culture. We're creating the universe's only culture. This perspective should fundamentally change how we approach our global challenges. Climate change isn't just a threat to human civilization. It's a threat to the universe's only known experiment in consciousness. Nuclear weapons aren't just a danger to our species. They're a danger to the cosmos's only way of understanding itself. The development of artificial intelligence isn't just a technological challenge. It's a test of whether intelligence can survive its own cleverness. The silence from the stars is both a warning and a responsibility. It's a warning because it suggests that most civilizations don't make it past the challenges we're facing right now. It's a responsibility because it suggests that we might be the universe's only shot at a conscious future. But there's also something profoundly hopeful about our cosmic search. Despite all the theories about why we might be alone, despite all the scenarios where civilizations destroy themselves, despite all the reasons to despair about our future, we keep looking. We keep building telescopes, analyzing data, asking questions, hoping for answers. The search for extraterrestrial intelligence represents humanity at its best: curious, collaborative, reaching beyond immediate concerns to ask fundamental questions about existence. It's a reminder that we're capable of thinking beyond ourselves, beyond our planet, beyond our current limitations. And maybe that's the real answer to the Fermi paradox. Maybe the reason we haven't found aliens isn't because they don't exist, but because the act of searching for them is itself the point. Maybe consciousness isn't about finding others like us. Maybe it's about being the kind of beings who would search for others like us. The universe might be vast and empty, or it might be full of intelligence we can't detect. We might be alone, or we might be surrounded by civilizations that have learned to hide. We might be the first intelligent species in our galaxy, or we might be the last. But regardless of the answer, the search itself tells us something profound about who we are and what we're capable of. We're the species that looks up at the stars and wonders. We're the beings who can imagine possibilities beyond our immediate experience. We're the consciousness that emerged from cosmic dust and learned to contemplate the cosmos itself. Whether we're alone or not, whether we find aliens or not, whether we survive our current challenges or not, that capacity for wonder and inquiry is genuinely remarkable. The silence from the stars isn't just a scientific mystery. It's a call to action. It's a reminder that consciousness is precious, that intelligence is fragile, that the future of understanding itself might depend on the choices we make right now. So as we continue to listen for voices in the cosmic dark, as we build ever more sophisticated instruments and develop ever more clever theories, as we grapple with the possibility that we might be alone or that we might be surrounded by hidden intelligences, we should remember what this search really represents. It's humanity's greatest expression of hope, curiosity, and determination to understand our place in the universe. The aliens might be out there waiting to be discovered, or we might be the universe's only witnesses to its own existence. Either way, the search continues, and with it, the most human of all activities: the quest to understand the cosmos and our place within it. The universe is vast, mysterious, and filled with possibilities we can barely imagine. And somewhere in that vastness, at least one species has learned to look up at the stars and wonder if anyone is looking back. That alone makes the search worthwhile.